She's asking what's a good place to read about periods.
About periods.
Yeah.
There's a good article by Constavich. David, I think you look up in Wikipedia article on periods. If you look at the references, it was the article.
No. All right. We'll continue with the second talk.
Can you write a little bigger today?
Yeah, Andre told me, I have this tendency of trying to fit things, on a single board. Let the writer. What I'll try is that I'll try to write bigger on the extreme boards because I notice myself it's hard to read those. Okay, so right, today I'll start lecturing on what's the workshops, the graduate school week title, which is p-adic functions. And thanks to my colleagues, things been quite well set to do something meaningful and not just kind of wave hands and say, just put a p to a L function and that's a p-adic function. So let me so the way the program will go, I'll first give the example of the Kubota-Leopold p-adic function, which is the p-adic analog of the Riemann zeta function. So that's like the first historic example, and also it's quite easy to set up. So you have already an idea. And then I'll do an interlude on explaining like some general philosophy, how it should work for motifs or Galois representations if you want. And after that, we'll focus on automorphic forms, which is the main focus of the workshop. So somehow the idea behind these things is that there's some general philosophies and conjectures, but in real life, you attack those through automorphic representations to do something, some actual theorems. But it's good to have the general philosophy, maybe. So about the Kubota-Leopold. Function. So I'll just take here result without proof, because first, well, after this, two proofs for GLN, and second, historically it was proven kind of by hand. So you can find this, for example, in Washington's book, cyclotomic fields. It's a good reference. There's no really point to spend much in the details. I mean, I kind of don't have a lot of taste for just formulas, so and especially writing on the board, small as I write, it's not very useful anyway. Okay, so the basic thing is exactly as this workshop open. So fix a Dirichlet character chi from and I'll directly take it. So it's a C-valued character, right? A Dirichlet character, but because it's a finite group, it falls in the roots of unity, and therefore I can fix an embedding iota p in QP bar. So I fix such an embedding once and for all, and actually the p-adic functions will implicitly depend on iota pi. I mean, changing iota pi, it's like changing the chi if you want. And assume that's important. Assume that chi is odd. So this means that chi of -1 is -1. And so there is a fact, which is that if you consider the L function of chi, which was already defined, if you consider the values at 1 minus k, k is at least 1, so this is a rational number. And actually, it also has good integral properties. So then we fix p, and I'll take it odd, just to avoid some issue with the type Miller character. Yeah, if you take the partial sums, these are in Q. But if you do there is a Z structure. If you take like the partial sums over sum of integers n congruent to a modulo capital N. But yeah, okay. And so people noticed already historians the so-called Stickelberg relations. I mean, they notice that when k is very congruent to k prime, the values are also very congruent. When k and k prime are p-adically closed, these two values are p-adically closed. And to put this in perspective with respect to Raghuram's talk, so here there is no period. So the period here is they're already algebraic numbers, so I don't need these u plus or minus kind of things. Right. So sorry. So this is for k. Sorry, for k even. So this is so basically the Riemann zeta function, the values at even positive integers is the power of pi over some rational number. But when you use the functional equation, s goes to 1 minus s, the values at odd negative integers would be there won't be pi anymore, so it's even better for interpolation. We get rid of the pi's if you want. Okay. And so the theorem of Kubota and Leopold, which in a way is a reformulation of all these congruencies that I did write. I mean, maybe I have a little bit of space here. So there is another like fact. It's a classical fact is that like you know that if k is congruent to k prime, you know Fermat's little theorem that it says that n to the k, like for n relatively prime to p, will be congruent to n to the k prime. So if k is congruent to k prime modulo p minus 1, like p to the sum n, so this will be also congruent to some n plus 1. So this is Fermat-Euler's theorem, and this doesn't really imply, but heuristically this implies that the L values, which are infinite sums of things like this, will be congruent, and it's a theorem that okay, I won't make it precise, theoretically closed. And I give a precise statement now. So these are classical facts about Bernoulli numbers. Yeah, that's a Bernoulli number. The precise statement is the following. There exists a function, what's called a p-adic function, so LP. Okay, so there's something like assume. Okay. assume that chi is different from the Teichmüller character. Do you remember this Teichmüller character from John Stock, or you already forgot it? This is like the C mod PC star character. Okay. Sorry. So there exists a p-adic function like this, so which is analytic in S in CP and characterized. Oh, yeah, we write small, sorry. By the following interpolation formula. Which is precisely for integers k at least 1. The value of this function at 1 minus k is equal, well, I just leave some space here, times the L function, so this is the complex L function at 1 minus k. And this is very important. So here you put this correction factor. So if p does not divide n, kind of p is non-zero, and you correct that way. So this is precisely, this is the Euler factor, or the inverse of the Euler factor at p. So you remove the Euler factor at p. And well, I cannot convince you right away why you should remove it, but what you really see is that, so this is analytic, this is p-adic analytic in this variable. This is p-adic analytic. Well, these are some just a bunch of p-adic numbers. I mean, they're in q bar, which is in q bar. They're just a bunch of numbers. But this thing is a function of k. I mean, you can consider the function k goes to p to the k, and that's certainly not analytic. The function on integers which to k attaches the k power of p, that's like very wildly exploding. So that's not analytic. So I'm saying that this can work with this or without this, but not with both. So I mean, I'm not saying that. I'm saying this correction factor, if such a statement is true with this factor, is certainly not true without this factor. So it's really important to put it or not put it, or put the correct factor, correct kind of factor like this. Okay. So that's the statement. And with respect to what we discussed, in lecture 1. So I explained Amis and Melin transform, and here I'm kind of going backwards. So I stated the theorem for analytic function, and what we explained in lecture 1 is that there is something called a Melin transform. Which okay, so this thing here will be the Melin transform. So mu is a measure of mu, and the Melin transform of mu is a distribution on characters on ZP star. Okay, so here you feed up a continuous character on ZP star. And the character you should fill up is this wrangle from John Stock to the S. Okay, this is the way you parameterize characters by S's. Okay, this is the way we say that the continuous characters here is the open unit ball. Okay, so you can apply what's called inverse Melin to analytic function like this of control growth. It comes from a distribution, and so this is a distribution on on ZP. And it's a fact that it's bounded. I mean, bounded means that actually these numbers here, their p-adic valuation, they don't have denominators. They're really actually these numbers here, once corrected, they're really in this intersect like ZP bar, if you want. And I also explained at the end of my lecture very quickly what's called a mistransform. So a mistransform takes a distribution and constructs a form of power series, which people call zeta sub chi, the zeta element, it's a function of t. So this thing, because it's bounded, the distribution bounded means growth zero. I mean, I probably didn't introduce the vocabulary. There was these admissible distributions which are of growth h, and when h is zero, this is called bounded distribution, and some people call this measure. When people say measure, sometimes they mean almost always they mean a distribution of bounded growth. And because it's bounded, it's really I mean, if you open your lectures, these were like a sequence of ANs which grow like n to the h. So when h is zero, it was just a bounded sequence. And when you think about it, what there's these things, these are really like formal power series where the coefficients are bounded. It's really the same thing. So this is called sometimes people call this the p-adic zeta. And this is called the p-adic L is more like an analytic function, and the p-adic zeta element is more like an element in the power series. Yeah.
So did we get this mu by taking the inverse Mellin transform of our LP, or do we have it to start with?
No, yeah, it's a good question. No, I mean, inverse Mellin only works like if you're in the image. I mean,
Okay.
oh, so no, you can. Okay. No, you can do inverse Mellin, but it's not clear that it's an admissible distribution. And the claim is that when you do this inverse Mellin, it's not just a wild distribution, it's a distribution which has controlled growth and actually has zero growth. Right, yeah. But you can also navigate here. So the way these are directly connected, if you want, is that this thing, when you evaluate it at 1 plus p to the power k minus 1 minus 1, this is LP. Sorry, it's really small here, but I said I'll make a little bit of exception for the middle board. And I forgot something here. There is a converse condition. I'm sorry. Otherwise, we have to put a lot more tabular characters. So you have to p minus 1 has to divide k minus 1. Sorry. So this is like in Johnstone. Remember, k was sorry. P was 11. Yeah. And so like 10. They were like the weights were shifting by 10. There is some subtlety otherwise, which is not very serious. You can do it on, but the main point is that so this I'm not sure we got to this kind of exercise in the exercise session, but this comp is really like a union of p minus 1 unit balls, and assuming that k is congruent to something about p minus 1 is basically that you work on one of those, and that's actually it's not the weaker theorem because these are unrelated. You have a family of p minus 1 distributions, like a distribution on dead ball or dead ball that have nothing to do with each other. So, like stating the theorem for one of the balls or for all, it's just a question of presentation. It's not a weaker theorem stating by putting this congruence. Okay. Okay, so that's historically the first one, and right. What you should remember is this factor that gets somehow we really kind of interpolate things outside the p primary part of the L function. Okay, so now I'm going for a digression on what people believe it's true. I mean, it's important sometimes in mathematics to have some grid in your mind to fit results that come in the literature. There are so many papers that are published every day. So Coates, who's one of the instigators of this p-adic function, and his one of his then students, Bernadette Bernariou, made some very bold conjectures about what should be a p-adic function in general. So a very short remark is so if you take M a motive, so this was very fashionable following Grothendieck's word, so to be a motive over Q with some coefficients. So for us, a motive over Q, so a motive is can be thought of like a piece of a proper smooth variety over Q, but a motive is supposed to have realizations, like a variety has étale cohomologies for each P, and those are supposed to be a conjecture to be fully faithful functors. So we can actually forget what's a motive and just consider its p-adic realization. Okay, so a motive has a p-adic, so I fix again P, the prime number. So what's a p-adic realization is V, which for me it's a finite dimensional like n-dimensional QP bar vector space plus continuous go of Q bar over Q action, which is geometric. What means geometric? It means it is unramified outside the finite set S. Okay. Such that it factors through Galois of QS over Q. So this is the maximal unramified outside a finite set S extension and output P to be in S. And when you consider V restricted to the decomposition group at P, which I denote by VP, this thing is geometric. So this thing is what people call PST, potentially semi-stable. And for today, actually assume it even crystalline. So crystalline means unramified at P. So it means whatever would be the Galois representation attached to a proper smooth variety which has good reduction at P. Okay, so that's totally sufficient for today's purposes, and actually even for what's currently the state of the art in the subject. Right, and well, and so okay, so it's very handy that Raghuram spoke about critical. So so attached to V there is a L function. The only difference with Raghuram is that I keep putting S as a second variable in the p-adic in the L functions. Just habit. but it's the same. There is a way to do a L function, which is to do the product P prime of determinant of 1 minus P to the minus S. You should put an L just because P is my special prime. L to the minus S times Frobenius et al. Acting on V invariant by the inertia, right? As John explained, the Frobenius are only well defined where the inertia is trivial, and up to conjugation, I'm taking a characteristic polynomial, so that makes sense. L inverse. Yes. So there is a notion of an L function, and so Raghuram explains of this L function. There is a recipe how to complete it at infinity. This recipe doesn't come from the Galois representation. Well, it could come, but it comes more naturally from the motive when you take its the Ram and Betty realizations. So there is a way to complete it. And so Raghuram explained that when you complete it, if neither L infinity of this in the dual, if neither of those has poles, then this integer S is called critical. And so there is a famous conjecture of the Levin in this motives volume that if M is critical, if M is critical for V, then for any chi-Dirichlet character, if you take the L function of V tensor chi at M and you divide it, the conjecture is there exist two periods, only two, and not as many as critical numbers, such that this thing is in Q bar, and even as Raghuram explained, one can be more demanding if your family of p-adic represent, if this has some rational structure, one can be more precise. And this plus or minus only depends on the parity of M and the sign of chi. I forgot some. Yeah. So I was not exactly precise saying that it doesn't depend on M. It depends only by like for the Riemann zeta by a power of pi. I can remove, I guess, the 2i because I'm putting Q bar on the right. Okay, so there is this, and concept and we were thinking what we're reflecting what would be a p-adic analog of such a object, and they come up with the following conjecture, which it's conjecture even today, even nowadays. There is conjecture, but there is a very strong insight in this. So they say that contrary to the Kubota-Leopold example, which is in dimension 1, and it's a little bit misleading because in dimension 1 everything's kind of, there's no much choice. If you're in higher dimension, you need an auxiliary choice. You cannot just talk about the p-adic function of a motive or the p-adic function of automorphic representation. You have to refine it, what's called. So their conjecture is that for each V in decrease of V, so decrease of V, this is a QP. If this crystalline, this is a QP vector space of dimension equals to the dimension of V. Regular submodule. So what's decrease? For those who know contains p-adic Hodge theory, it's like one of the first things, so they obviously know. And for those who don't know, this is just a QP vector space with Frobenius operator phi. So this kind of a Frobenius, which somehow the idea is that when L is not P, unramified really means that there is a Frobenius acting on the vector space. And when you consider p-adic representations, I mean, they're always ramified at P, so you cannot really make a Frobenius act, but on V, but you can make it act on decrease of V, which is some other object. So it's some kind of a non-trivial semilinear algebra involved. And this Frobenius actually will have this as a Frobenius module. If you okay, I'll say this later, but so in the Dirkstock there were these attack parameters, and if V comes from Johnstock from the p-adic representation attached to automorphic form, then the eigenvalues of this V will be this attack parameters. Okay, probably I'll specifically get back to this in a moment, but basically, so this is a simple P module, so it's just this is a module is basically just like a sum of QP times unramified alpha I equals to 1 to n being the dimension, which is the sum of characters where the Frobenius acts by alpha I, and a regular submodule is just you choose a bunch of those, and the regular means that so what means regular? So it's a P submodule, so it's just you choose a bunch of these eigenspaces for P, and the regular means that you want to do the composition from D, submodule of this decrease of V, and this decrease of V actually it's isomorphic to the RAM of V, and this thing has a filtration, so this thing projects to it's a filtered module. So all these things are kind of very basic things in p-adic Hodge theory, but if you have never seen p-adic Hodge theory, you can just like close your ears just for a minute. So a regular thing means that you have a space with canonical filtration, and you want like this sub to be isomorphic to the quotient. So there is some numerology involved. So I don't know, like, are there like many people having looked at Denis' paper amongst you guys? Okay, so maybe I skip this comment. This is p-adically mimicking the way Denis sets up the periods with a sub and a quotient. But okay, let's skip it. And so then just remember that you need, in addition to V, you need this combinatorial data. So choosing a certain number, a subspace of a certain dimension, but it has to be phi stable. So this is like phi stable. So this amounts to choosing a bunch of among these n numbers. And you understand why for covalent we don't need this, because it's just a line. So and the numbers are given. So it's either choosing the whole line or choosing 0. I mean, in either case, you don't have a choice to make. But if you're like 2-dimensional, you have to choose a line, that's already like a choice. Okay. Right. And so they conjecture that well, that there exists a p-adic function, but it's really attached to V and to D. Analytic in S. Or equivalently, like mu, which depends on V and on D, distribution on CP star of controlled growth. I'm sorry, distribution on the characters. Oh. Yeah, like this of control growth, so admissible of some growth, such that when you evaluate this distribution at any Dirichlet character, ZP star. So conductor, I mean, I should say conductor P to the some power, conductor P to some power, P power conductor. And if you put the cyclotomic to some power J, where J was M, actually, I switched to be consistent with Raghuram. So this is critical. Well, you get exactly the L function of B tensor chi at M divided by these delete periods, plus or minus depending as in Raghuram stock, times this local factor at P. So this depends only on VP. So VP, remember, is the restriction to on chi and on M. So this is this correcting factor. So this is the correcting factor at P. Oh, sorry, and I should put D, of course, D and chi. So the correction depends on this D. There the correction was just 1 minus chi P to the k minus 1. So this really has the same flavor as Kubotta-Leopold. We have some distribution or some similarity function. We have a bunch of algebraic numbers. You can see as p-adic numbers. So these are just a countable set of numbers. And to fit them together, we need this function, which is a p-adic function, but it's not an analytic function. It's really somehow that the product becomes an analytic function, exactly like there. Okay, and so this is the framework in which people think of p-adic functions. Yeah.
Zero conjectures on the exact order. Are there conjectures on the exact order of the distribution?
The order is supposed to be related to the variation of the alpha i's that participate in D. So D actually, okay. So D here, it's really like you should think it. Okay, so this is only if this is what's called p-regular. If the alpha or I are pairwise distinct. Sorry, this really getting smaller now. You want a fixed module, and if this is a semi-simple matrix, a submodule just means you take a bunch of eigenlines. So this is just D is just a direct sum of QP, and then the character unramified alpha I, and just alpha I is in some subset capital I in one end. Okay, and so the control growth. The answer is depends. The precise growth depends on the p-adic valuation of those alpha I for I in I. But I don't know a single theorem which says that the growth is exactly this. I mean, it's at most. The theorems are always like the growth is at most such growth, like maybe when the growth is one can show by hand it's not 0. But like when there's a theorem claiming that the growth is at most 10, I mean it could be 9 a priori. I mean there is. Okay. Okay, so after this long introduction, maybe I go back to the middle board because it's important, and I explain. I explain one very general case which is known for automorphic forms. So what I want to say is that there are many general conjectures even before the p-adic world. For example, Artin's conjecture, which says that the L function attached to an Artin representation is analytic. And it's a functional equation. And this kind of motivic conjectures, the only cases they are known, and when there's an automorphic interpretation. Okay, and same is for p-adic function. So I'll talk about p-adic L functions. attached to automorphic representations. Right, so. Right, so these are the only cases where we can prove this conjecture of cause and value is when V comes from so henceforth kind of assume that V is V pi, like the V pi from John Stokes. So John explained that so this is like a representation from Galois of Q bar over Q in GLN Q bar, where pi is a regular algebraic cuspidal automorphic representation, right? So regular algebraic, this is the cohomological from Raghuram-Stolk. This means that it has it contributes to the cohomology. I mean, to this GK cohomology, this relatively algebra cohomology in with respect to V lambda, right? I mean, so this means that it exists lambda dominant. So lambda is like lambda 1, lambda 2, lambda n, such that pi contributes to the cohomology for this SGK. I mean, K pi, I mean, this can depend on pi of V lambda joules. So I'm sorry, I mean, Raghuram's M's got V's, and I use mu for the distribution, therefore my weights are lambdas. But aside from this is the same, so this is regular algebraic. C is cuspidal. And as John explained, in 2020, we to reach such pi, we know that there is a Galois representation, right? So I mean, we don't know the modularity theorem that each, but also we know that to each pi we can attach such G pi, and there are conjectures actually that each Galois representation, which is geometric and irreducible, should come from an automorphic form like this. So in a way, we are not losing generality by shifting to an automorphic setting. Okay, we're not doing a particular case in conjecture, we're still doing general case. Okay. So one thing that we learned from this conjecture is that we have to do a refinement. So we need this regular submodule or something something like this. So we will not be able to attach Galois representation, sorry, a p-adic function just to pi. Okay. And so before getting into that, I just okay. So in what follows, I want to explain what's called the conjugate symplectic case, or the symplectic case, let's say.
Sorry.
Yeah, go ahead.
So I'm just a little bit confused about the statement of the conjecture. So there, so we have like D, which is like regular submodule.
Yeah.
And then there exists some LP that is dependent on VD,
Right.
V and D. So what is the relation of that LP with that mu dV? Is that the Merlin transform? Some
Your confusion with respect to the D or something else?
just confused, like what is the relation between that LP and
Oh yeah, this is just the Merlin transform.
so that LP is
Yeah, well, I say equivalently, I mean, like here, the triangle I wrote there. We were shifting there, these three different languages where you do p-adic functions. You either do distribution, okay, so usually the way it goes is that you always do distributions, because that's the way you construct things. But if you want to differentiate, I don't really know how to differentiate the distribution. So you first use the Merritt transform to get the analytic function in X. Then many people are interested in bulk auto conjectures and be able to differentiate like derivatives of L function or p-adic function. So then you go here, Merritt transform. Or people in the Iwasawa theory, sometimes they like power series, like CP double bracket T is called the Iwasawa algebra. So then you do a mistransform and you consider, but the most malleable notion is just the distribution. So distribution of certain growth, okay? So it's a linear functional on local analytic functions, okay, which has a certain growth. Okay. So if this eases your mind for each time I write a p-adic function, think distribution, okay? Okay. Right. So this is a very general thing, but I want to say that in this generality, p-adic have only be constructed for n at most 2, and very recently n equals 3 by Loeffler, and it's a preprint, and Williams will be here next week. So one thing that people often assume, even with respect to the first case is known of this theorem of attaching our representations to automorphic forms, is to assume that representations are essentially self-dual. Okay, so henceforth, assume that there exists eta, the initial character, such that the contragradient of pi is isomorphic to pi tensor at the inverse. So this is what's called essentially self-dual. Okay. So when you have an essentially self-dual representation, this induces invariant bilinear form of V by the symmetry, and it's easy to check that this this bilinear form B, when you do the double dual, when you do the dual, it's the form itself of the scalar. So if V is irreducible, so if you assume that, so assuming V irreducible, we don't have to assume this, but this is just to motivate what I'm saying here. When you have an irreducible space with a bilinear form, whose transpose is lambda times the thing, this form has to be either symmetric or antisymmetric. Okay. Vj has to be like plus or minus B. So henceforth, we'll assume that the form is symmetric. So henceforth, B bivial is assumed to be symplectic. Which implies two things. First, it implies that n should be even, because to have a non-degenerate symplectic form, you need the dimension to be even. So actually n will be equal to n henceforth. And actually this implies also that phi so pi is automorphic representation of GLN, but actually this implies that pi comes from G spin 2n plus 1, and we don't need to know what it is. We just need to know that this means that P pi has a Shalaika model. Okay, and this will be somehow, it will be mentioned when it's used in what comes after, kind of. So for now, just remember that pi is of some kind of a special type. Okay. Are there some questions?
P rather than GSO? Why is it G spin rather than GSO? But why would you take the coverage?
What do you mean? Why? It's you're saying. Symplectic. Okay, symplectic means if you want that the Galois representation is in GSP, right? Because it preserves the symplectic form, and the dual group of GSP is G spin, right? Yeah. So this is the quasi-discrete form. It's a little bit bigger than the cover. Okay, so right. Okay, so we'll have one last assumption before I state a theorem, which is to many people. Finally, assume that for all L, phi L is spherical. Right, so as in the Dirichlet, this means it has a invariant under GL2n. Now it's shifted from n to 2n of CL, right? That's a line. So under this assumption at P, so I'll explain now what's this D. I mean that's what in automorphic, this regular submodule from p-adic theory is called the p-adic refinement. So the refinement D amounts to the choice if okay, I'll explain what should be UP stable line, okay, of a line in phi invariant by JP, phi to the JP. Which is UP, and UP is JP. Okay, so in this GL2n representation theory with Shalaika models, there is one very pleasant feature, which is that everything I'll ever write will be by block. So you can take all the time GL2 if you want. But believe me that this carries over GL2N, okay? So JP is the GLN ZP. It's what's called a parachoric subgroup, MNZP, P times MNZP, GLNZP. So this is like for n equals 2. This is exactly the gamma 0 P subgroup, which we saw. UP is exactly the UP we saw as well. And so refinement is just choice. So you see, if you take the invariant by the maximal compact, this is a line. So if you take an invariant by a smaller subgroup, well, so you can, so this is an exercise if you want. Yeah, I didn't give many exercises. There have already been quite a few in the previous lectures. This has dimension. Choose 2n n. So for example, when n is 1, this is a two-dimensional vector space, and people usually know that the refinement for a modular form is you take the Henke polynomial, so the characteristic polynomial of UP, so that's maybe an exercise for GL2. So when I say GL2, this is really n equals 1. So the characteristic polynomial of UP acting on this pi p gamma 0 p or k 0 p relation is this x squared minus apx plus p to the k minus 1. So assuming that this polynomial has two distinct roots, alpha and beta, right, which conjecturally is always the case. That's a conjecture that there is no really modular forms with a double root. Choosing this D or this refinement is choosing between alpha and beta. And those who have done a little bit of modular forms, especially p-adic aspects, know that there is this destabilization one always does with the modular form. One does this, right? So this D, like this choice, like for GL2, this choice of D is really like choosing between f alpha, which is f of z minus beta f of pz, or f beta, which is the same thing with alpha. So this is a way when you have a modular form of level prime to p, to put it in level gamma 0 of p, but not in an arbitrary way, in a way so it's a UP eigenform. So these are UP eigenforms. So this one, if you hit it with UP, it's an eigenform, so it's alpha. So this regular submodule and its interpretation in local representation theory. I mean, Nadir will say a lot more about Ivakovic algebras and such kind of things. But this is really the correct generalization of what people call the p-stabilization. Okay, so this is what's called p-stabilization of a modular form. Okay, so as time is running fast, let me state the theorem. I'm hesitating whether I should do it on the middle board or let's see. So here is a theorem which is due to many people. So first, maybe Ash and Ginsburg. And okay, I'm saying like when n is at least 2. I mean, for n equals 1 is a older story due to Mani and Maser almost 50 years ago. But in this form, is due to Ocean Ginsburg, and then to Yanushevsky, Ragoram, and myself. And in the formal stated, it's been reworked with the collaboration of Barrera and Williams. And if you want to relax the spherical assumption, you have to add ongoing work with Georgia. Okay, so okay, so assume so this pi tilde, which is this pi with the choice of this alpha p, so alpha p. Sorry, did I write this? Alpha p is the so okay. So alpha p is the on which is I didn't finish my sentence here. Wow, which is UP stable. I'm sorry. Eigenvalue alpha p. Okay. So a refinement is you take a line which is UP stable and you call alpha p the eigenvalue by which UP acts. So assume that this and the refined version. Assume first it's regular. So regular means so many things in this mathematics. So it's nothing to do with the regular module. The regular here means that alpha is a simple eigenvalue. So regular means that if you take this pi p, if I take invariant by the spherical, by the maximal compact, this will be a line, but I take invariant by jp, which is smaller. Now UP acts, so I can take generalized eigenspace. So generalized eigenspace this is finite dimensional. So this is linear algebra. Just I do Jordan decomposition. I take generalized eigenspace. So I mean, it's very important not in this p-adic analysis things not to take eigenspaces but generalized eigenspaces, because when you go to Banach modules, etc., that's the only thing that makes sense. You cannot really do a direct decomposition to eigenspaces, but you can always do with generalized eigenspaces. So if you just say that's like if you just put the usual bracket, that's one dimensional, that won't get you like very, very further. So you need this to be a line. So of course, if alpha p is a simple root, then obviously, well, that's what this means. Okay. Right. And of course, I didn't repeat. So this is as above. I mean, so this pi is as above. So as above means it's a regular algebraic, symplectic. So this S is for shalike or symplectic. It's very handy. They mean both. So it's a regular algebraic symplectic cusp-automorphic representation of weight lambda. And this lambda, it's like this, 2n. And Ragoram explained that this notion of purity, which is that lambda I plus lambda 2n plus 1 minus I should always be the same number, which I denote double like this, exactly as in the GL1 story of Ragoram. Okay, so you assume this that. Okay. Then let alpha p circ to be the co-character attached to lambda, evaluated as PPP 111, I'm always the same number, and like this and like this. That's alpha p. And denote HP to be the p-adic valuation of alpha p. Okay. finally, assume that pi tilde is non-critical, and I'm pretty much sure I'll explain this next time. Then the theorem, if there exists, there exists a distribution mu pi tilde, a p-adic distribution on CP star of growth HP. So it's always, this is always a finite number. This is always a finite positive rational, because the alpha p, there's no zero eigenvalue when you act on UP. When UP acts as a fact on uniformly fixed vectors, it's a monarchical, there's no zero eigenvalue. So this will be of some finite growth. Yeah? Such that for any chi Dirichlet, for any chi from C mod p to the beta z star to p star, and for any j critical, sorry, j is m, for any n. So what the critical interval here is this has a different meaning from there. It's the integral of integers between minus lambda n and minus lambda n plus 1. So because of this symmetry, they are centered. So like the middle one have a specific role. One has, and that's unless you have questions, probably the last line I write today. What has the following formula? So mu p tilde, when you evaluated this chi cyclotomic is just the character that sends CP star to CP star, which is the identity character if you want, to the n. It's a very simple formula. So it's, if you write it completely, it's a precise formula. It's the number of elements it's somehow the volume of the GLP, so the same minus okay times p to the n m plus n square minus n over 2 over alpha p to the power beta times the Gauss sum of chi to the power n times some immediate z integral times exactly Devin's conjecture of algebraic values. So pi tensor chi evaluated at n plus 1/2. So in this normalization, the critical range are half integers, just automorphic normalization modulo like this. And I can add the word here unique. And that's a nice exercise, which actually you can look at my students' forthcoming thesis for the NGN. He wrote a very nice lemma that actually, if you have a distribution of a certain growth, you should know on ramified characters. Here this formula is only correct if beta is at least 1. So you know the distribution everywhere, but you don't know it at the trivial character. But so the exercise, which is a lemma, which somehow is not in all these classical references for some reason, is that this determines the distribution. It's not very hard, but amazingly well, probably somebody here will tell me that he's seen it somewhere, but my student didn't find it, so he proved it. So if you have, this is obvious for growth zero things. But for distributions of growth something, the fact that they're uniquely determined, if you know them on all but finitely many characters, that's, well, okay, so that's true, but it's in this thesis, so thank you very much.
Sure. So I guess what's the end goal of associating these p-adic functions to our representations?
Oh, that's a very good question. I can say something quickly, but I was going to fill one of my 2 remaining lectures with comments like this, but yeah, okay, no, let me say something very quickly. So I mean, one reason is that, I mean, if you're interested in Vulcan couple conjectures, I mean, okay, I don't know, I hope everybody's not starving. Basically, you know, there is the Vulcan conjectures, which said that the order of vanishing at S equal 0 of the L function of some motive, right? It says that this is supposed to be the dimension of a Vulcan-Selmer group of I hope I didn't screw up the ones and zeros here. Okay, well, what's happening is that this is something analytic. This is something kind of p-adic already. So a priori, it's much easier to show that that thing here is to relate it to the order of vanishing at S equals 0 of L D. Okay, so there will be this D now here. And S, and actually in my last lecture, there is this trivial zero conjecture. So there are exceptional zeros. The same way the Riemann zeta function gets some automatic zeros at negative integers. This thing gets some automatic zeros. Did I erase this board? Well, I erased exactly the only useful board for this comment. There was this. You remember the calculation? There was this 1 minus chi of p to the minus s thing in the Kubota-Leopold. So you can imagine that this thing can vanish. Right? Okay. So I'm saying in today's knowledge, the only way to prove new cases of Birch-Smith and Dyer conjecture is through p-adic techniques. So yeah, we have this comment with Andre in our common paper that whereas like p-adic function had been first introduced because Maser Theta 1 was looking for a p-adic analog of BSD just for fun. Today's progress on the initial conjecture is mainly through this p-adic variance.
Oh, okay, thank you.
Okay. Okay, go ahead.
So the self-duality hypotheses here.
Right.
So is the reason, so like, I mean, like you need these for like the construction of Galois.
Yeah.
But is what you're saying here that like the current methods for constructing p-adic functions?
Yeah, here
like
you need them
also
even more.
What?
Here you need them even more. So my comment is over there. In this generality, p-adic function actually Loeffler and Williams, and Williams will talk about this next week if some people are still hanging around. But he has a preclinical archive, I believe, already. So until like a few months ago, nobody knew how to do this even for GIL3 without the self-duality hypothesis. So yeah, I mean, yeah.
Let me actually answer.
Yeah.
I had something more. It's that self-duality applied to GL2L. There is, in all these arithmetic applications, there is some analytic theory of L functions in the background. Here, because of that condition, there is a integral that Jacque and Friedberg studied. This GL2N cusp form you integrate against the diagonal GLN cross GLN. And that, in fact, gives the standard L function. that integral gets interpreted in cohomology, which then leads to this theorem. And for the JLN cross JLN period to be non-zero, it needs a Shalaika model and all this. That's where the subtheory comes.
Yeah, and like as a closing remark, I mean, when I say this generality, like there are many other, if you Google p-adic functions, there are a lot of p-adic functions, there are Katz p-adic functions, there are Rankin-Selber p-adic functions, there are some isotopes. All other p-adic functions in the literature are measures, they're like growth zero. This is the only, to my knowledge, method where one can construct p-adic functions for like a possibly not bounded, so for with some growth. So yeah, in a way it's restricted, but I'm saying given the generality, it's still quite quite a good compromise.
All right. Let's break for lunch then, and we'll get back at 2:30. We'll shift by half an hour, so we can you know, get enough food. It's pretty good that we have Tuesday and Thursday,